Well, there it is. That's the gear hobbing spindle in action. Right now it's set up for 71 teeth, a 71 tooth gear, which is one of my prime number gears. But that was mainly because those were the gears I had. I found that the new setup was a little more sensitive than I expected to pulses on the index line, probably due to the universal joint setup that I have, which is awkward at best and usually close to the limits of its angularity. But the addition of a small flywheel, which I happen to have sitting around, took the torsional inputs away. This is the feed train. This is set up for about 50 to 1, which gives me roughly 6 thousandths table feed per revolution of the spindle. This is the lead compensation train, which is working, but I mean, it's really slow. I'd have to speed this up like 10 times to really see it in action. The table feed is connected. You can see the reversing tumbler there, and everything is working pretty much as it should. That's the feed drive. Switch to neutral. Just disengage the gears. And now what we can do is put my little angle thingy on the chuck. And we can take it back the same way. And that's the lead compensation. Well, this is the second piece off, and it came out pretty good. It's 13.3 degrees right hand helix, because that's the lead that I had available with the gears I had on the machine. So I just decided to go ahead and make that. The first one came out bad a couple of times because I got the blank the wrong size. All part of the learning curve, but when I got that sorted out, it produced a nice clean tooth profile that seems correct. The metrology guy got laid off, unfortunately, so I won't have a lab report anytime soon, but it looks decent. Not bad. holding here is my first reasonably successful helical gear. This one's in aluminum, and it's 40 teeth, 13.3 degrees, right hand, and altogether not too bad. But something strange happened when I tried to cut a gear in steel. Now, superficially, this looks like a good helical gear, but if you look at it, there's a distortion in the tooth on kind of the leading edge and the trailing edge of the tooth. Here in the center, it's actually perfect. Good profile, nice and straight. Everything's working with the lead compensation system, but what I'm getting is a loss of position control of the chuck. When the cutting force is unbalanced between the two sides of the groove between the teeth, and it's in one direction coming in, and it's in the opposite direction coming out. And really, I think what's happening is as the tooth on the hob passes through this slot, it contacts one side first and the other side later, and as a result, it deflects the workpiece just a little bit that way because of the play that I have in the spindle, which seemed like it was fairly slight. But the fact is, this kind of asymmetrical load is causing a deflection of the system that causes the tooth to go crooked. This is what one of my friends from the past would have called a moment of self-nullification, because it's clear that what's happening is a result of the compliance that I build into the system by putting the differential directly in line and downstream of the 40-to-1 drive. Now, this does a really good job of positional control. There's almost no play in that whatever. But the differential itself, by virtue of the bearing system and the play in the gears, is actually causing enough, it's allowing enough deflection that I lose positional control across the face of the gear. Now, it's not too bad with the aluminum, although there's still some evidence of that because the cutting forces are quite a bit lower. But when I try to cut steel with the higher cutting forces, and again, the cutting speed and the feed were exactly the same in both of these cases, in situations where the cutting force is unbalanced between the two flanks of the tooth, you get a deflection. And the same thing happens on the outside, or on the outgoing end of the tooth. And in fact, you can kind of hear it. The cutting noise becomes a little bit more, there's kind of like some impact going on there. I can't feel it in the chuck, but in the end, I think it's just forcing the system to deflect one way or the other, and that's enough to screw up the tooth. So here's my conundrum. This is obviously not too bad. I can live with that, but I want to be able to make steel gears, and this setup is just not going to work. I mean, the workaround would be to put a sacrificial gear on either side of the part that I care about in the middle, but that's going to get old in a hurry. So what I think I need to do, and as sad as I am to admit this, I need to acknowledge that the design for this spindle that I fixated on has an embedded defect that's not going to allow it to be successful. And what I have to do is rip all this stuff out, replace the two-piece shaft that's in there with a solid shaft that goes from end to end, which has got some pluses from a mechanical stability standpoint. And I have to design a differential to go here on the input side of the box that will be upstream of the 40-to-1 and upstream of essentially the pretty much complete torsional isolation that you get from this worm gear. So that's a tough pill to swallow. I thought we had this worked out, but I can tell you in general the way this is going to look. I'm going to keep the, excuse me while I readjust the camera a little bit here. I'm going to keep the lead compensation train because the input side of that and the output side is all usable. I'm going to poke this shaft through to the other side and do whatever I have to do here to install a differential on the input side of the box. I haven't figured out exactly what that's going to look like yet, but I'm thinking that I may try to make a spur gear differential here rather than a bevel gear differential, because I believe I can make one that's fairly compact, might be 6 inches in diameter, which I can accommodate here, and I can drive that maybe with a couple of gears on this side of the box and get the lead compensation that I need without the creating this kind of play in the system. And the reason why it's important to have it here, I think, in hindsight, being 2015 at least, is that variations here only show up here as 1/40th the magnitude. So if there's a little bit of play here, you know, some fractional degree of lash in the differential, whatever that is gets divided by 40 when it comes to this. And I think the actual angular deflection of this worm gear is far, far less than what I'm seeing now with the differential in line. So that's a bitter pill, but at the same time, this is how I learn things, by screwing up. I think I put it right in the title of my channel, and it's a continual cycle of experimentation, failure, and diagnosis and correction that drives almost everything I do. So I should be celebrating this failure rather than feeling kind of crappy, which I actually do. But on the other hand, I know what comes out is going to be better. So anyway, I am sharing this particular conceptual failure with you for the benefit of everyone who wonders how I do this stuff. This is the way. I try things, I screw up, and I figure out how to fix it. And it's made me kind of fearless in a way, but at the same time, it doesn't mean that I don't appreciate a good success every now and then. Thanks for watching. I hope this video has been informative for you. There'll be more in the future about how this is going. The machine itself works, the drive system works, the lead compensation works. It's the conceptual failure of putting the differential in line at the lowest speed in the system that's causing this particular issue.